Hello. So today we'll be basically having a model tour. We'll go through a bunch of different models, try to understand some upsides and downsides of many of them, and see if we can come up with solve the problems that arise from many of these models that we see. Prerequisites for this: I assume you're familiar with what a neural network is. You have heard what backpropagation is. You have seen the gradient descent algorithm. I also assume that you have familiar with what word2vec is, the architecture, and the video that I had presented last. If not, please go watch that first. It will be helpful. And you also have some idea of basic maths, what you would do in MA 1101, some amount of like what a gradient is, for example. And you remember some amount of vectors and matrices from JE. Okay. So to start off, last time we looked at this simple neural network to learn embeddings called the continuous bag of words approach, where we took a bunch of words, masked out a middle word, took 4 words before the masked word and 4 words after the masked word. And then what we did was we created these one-hot vectors. For example, we took these words and assigned them numbers and set the entire vector to 0 and kept only one number as non-zero. We set it as 1. And then we multiplied this common projection matrix W with these one-hot vectors. So a vector into a matrix will give you a vector. We took each of those vectors and added them together to get the hidden state. And we multiplied W prime, another matrix, with the vector HI to give the output probability, to give a probability distribution over the output words. And we figure out which word is most probable. And with that word, we check whether that is the masked word or not. For example, in our case, last time we looked at this sentence, a thing of beauty is a joy forever. We masked out joy and checked if the model is able to guess the word joy or not. So now how LLMs like ChatGPT work is, instead of predicting masked words, what it does is it predicts the next word, which makes sense. You can predict, now given n words, you predict the n plus 1th word. Now you give the n plus 1th word back as input. You predict the first, with the first n plus 1 words as context, you predict n plus 2 and so on. One by one, you predict one output, give that output back as input and continue so on. And this kind of approach is something called the autoregressive approach. So let's see if this particular architecture, this continuous bag of words, can be used for, in an autoregressive way, to create a language model of sorts, something that can generate text. So let's see what will happen. Suppose we send in a thing off, it processes a thing off, gets a hidden state that has context of only these 3 words, a thing off. And suppose it predicts that beauty is the most probable word. Then next we send in thing of beauty. It processes only thing of beauty, doesn't have access to the word a, gets a hidden state, multiplies it, gets an output, suppose it's is, and so on. So we send 3 words at a time. Each time we take the output from the previous generation as the input and go on. What do you think are the downsides with this approach of using this architecture? Do you think this would work well? So let's think about it through a couple of examples to see how the model reacts with certain situations. So as a first example, let's see what happens if the ordering of the words are changed. Suppose you send a thing of a thing, and the model predicts beauty in one case, it should predict beauty in all cases. Why is that, I think? We go back to the architecture, right? You created these one-hot vectors v1, v2, v3, multiplied them into a projection matrix, right? So let's look at how that works. You're doing v1, wv1 plus wv2 plus wv3 plus dot 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 wvn, right? Now let's see if we can do something else about it. So each of those vectors you're adding one by one. I can take the W matrix common and I can do V1 plus V2 plus dot 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 plus Vn, correct? And if I'm doing V1 plus V2 plus Vn dot dot up to Vn, the order doesn't matter because addition is a commutative operation. I can do V1 plus V2 plus V3 or V1 plus V3 plus V2 and I get the same result. So this neural network is not taking into account the ordering of the words. And in all cases, you'll get the same probability distribution. This is clearly a big issue because if you take sentences, obviously you would know that if the ordering of words in a sentence, if the subject becomes the object and the object becomes the subject, the sentences could completely change in meaning and could be completely nonsensical. So this is something, a point of significant concern, that addition is a commutative operation, and because of that, the neural network isn't learning any ordering. And because it is not able to represent any ordering in the final words also, it doesn't know any ordering. This language model cannot predict sentences having order in its text. Now let's look at another example. Suppose we have a relatively long sentence. France is a democratic republic with French as its lingua franca. So we saw that each time it's processing only 3 words at a time, right? So it's processing only 3 words at a time. Suppose it has processed France is a, it generated something. Then is a democratic. Suppose democratic was the word generated. Then a democratic republic, and finally democratic republic with. By now, the hidden state of this continuous bag of words model is remembering only the 3 words that it is given access to. And France is not in that list. So suppose it is about to predict a language, any language is equally probable. And that's a problem. We can't have it generating that Hindi is the lingua franca of France, for example. So this is a big problem. A, it doesn't know sequences, and B, it doesn't keep the order of words. So no history and no order. And now actually with this no order thing, you kind of see where the name is coming from. It is called continuous bag of words. Whatever words come in, V1, V2, Vn, it just treats them as a set, not as an ordered group of words. And HI knows only about the inputs that are given to it. So let's think, what kind of modifications could we do so that we retain the information across time steps, right? So what if we do something like this? We know HO has information about V1, V2, Vn. We know H1 has information about Vn plus 1, Vn plus 2 up to Vn. And suppose we added this connection between HO and H1. So now H1 will have information about both V1, V2, Vn and Vn plus 1, Vn plus 2 up to Vn plus V2n, right? So this makes sense. This probably might be a way that we be able to, maintain history of words. Again, just to refresh your memory, H0 and H1 are vectors. Why? Coming back to here, we have V1, V2, Vn, which are one-hot vectors. That's multiplied into a matrix WXH. WXH is a matrix. The matrix WXH into V1 gives you a vector. The sum of those corresponding vectors for V1, V2, Vn are added together to get H0. So H0 is a vector. This vector H0 is multiplied with WHH to get H1. Okay, in all of this, I have skipped the bias terms in the activations. Those are necessary. If those are not there, like what we saw in the previous video, all of these would just be linear information, and that's not really that useful, it turns out. You need non-linearities, non-linear relations to model complicated things like language. So again, coming back, our problems were we had no history because each time it processed only n words at a time. Now that is handled with the WHH matrix. And second thing, there was no ordering between the bag of words. So any idea how to resolve this? One possible way we can do this is, instead of treating a bag of words, suppose we had a bag with size 1, right? If you had a bag with size 1, there's only one possible ordering. Otherwise, if you have a bag of size n, you have n factorial ways to arrange everything, all of that, right? But if you have a bag of size 1, you have only one way to order the word. So the ordering point is moot. So with these two modifications, we end up with the architecture, right? Let's just look at it. We take hi. The hidden state hi is now dependent on the hidden state from the previous time step and the input from the current time step and a bias term. The bias term is common for all time steps. The WXH matrix is common for all time steps. The WHH matrix is common for all time steps. So in this way, you are getting the history and the information from the current input to generate the hidden state. Whole thing is obviously has an activation function applied. Now that hidden state is multiplied with a matrix WHY plus a bias term by to get and pass to an activation function to get the output y. So this y output is depending on history, and in turn all the inputs x that came before it and the previous input x via all these connections that we saw. Browning question, which you could answer on the group. Would this ordering issue be solved if you didn't have this activation function? Because addition is still a commutative property. What advantage is this activation function that is applied after each and every time step doing? Think about it. Write your thoughts on the group. It'll be interesting. I'll keep note of who's answering, right? This architecture is something called an RNN. And RNNs can do pretty crazy things. For an example of all the crazy things it can do, you should go to Andre Kaparthi's post. I've linked it in the resources doc. Please have a look to see how, for example, a character level RNN, an RNN that processes only one letter at a time, is able to generate text that is similar to Shakespeare. Interesting. So have a look at that. So now the thing about RNNs is it can be configured in a bunch of different ways. One thing is what we saw just now. For every input, it generates an output, right? And that output is passed also to the. So okay, just now we did not use the output also to affect the hidden state. Maybe that is also possible. The output can affect the hidden state, the input can affect the hidden state, and the previous hidden state can affect the hidden state. You can also configure it for something as it processes all the inputs together and then generates all the outputs. Why would this be useful? For example, if you're doing something like translation, suppose you're translating Hindi to English, the ordering, the subject, object, verb ordering is different in both languages. So you need to maintain the meaning, but the length of the words, the length of the two sequences could be different. The ordering within the sequences could be different. So that freedom you should have without changing the meaning. And to do that, what you can do is you can pass one RNN. You get x0, you get h1, h0, h0 and x1 are used together to get h1, h1 and x2 are used together to get h2, h2 and x3 are used together to get h3. Now h3 has information about x1, x2, x3 and x0, and using h3 vector, you can generate the outputs h0 prime to generate the hidden state h0 prime. That generates the output y0, right? Now this y0 and h0 prime together, you can use to generate the hidden state h1 prime along with h3, which gives the context of the original word, original language's sentence. Now y1 and h1 prime and h3 together can be used to generate h2 prime. Similarly, y2, h2 prime and h3 can be used to generate h3 prime and so on, right? So this is quite powerful. Now you can do translation, you can handle sequences of multiple lengths. You're able to get a vector having the meaning of the entire sentence. Pretty crazy. And you're getting history and you're getting the ordering is respected. So let us see, maybe all things are not roses. Maybe something is wrong. First thing what we can think of is, suppose it's doing a language translation task, and you know, sometimes there are one-on-one parallels to the words and sometimes there aren't. So all the time, the model is given context of only H3, which has context of the entire sentence. Maybe a little bit more context about the last few words and not the first few words. So how can you, for example, be able to represent, for example, suppose at some point of the say translation task, you want to focus on this particular part of the text and some other part you want to focus on some other part of the total text. How do you do this? That's one question we don't know how to do, right? Right now we are doing only common representations. So can you think of some modification that you can do to be able to focus on different parts of the input at different times? To give a clue, you can think of H0 and H1. H0 has information of only X0. So if you want to focus on H0, somehow you want to focus on H0. Suppose you want to focus on X0, you want to somehow focus on H0 more. And H1 has information about X0 and X1. So maybe if you want to focus on X1 more, somehow if you can focus on H1 and remove out the H0 component, maybe that can help you focus on X1 more. Something like that. So let's see, one way to do it is instead of passing only H3, we pass connections from H1, H2, H3, everything to the output part of the RNN, right? So now you have one scaling factor, alpha 0, alpha 1, alpha 2. Alpha 0 scales input H0, alpha 1 scales input H1, alpha 2 scales input the hidden state H2. And suppose you have all of these knobs that you can tune, that you can scale by different amounts, then at different stages of the generation, you can focus at different parts of the input. Suppose at generating Y0, you need to focus on H1 more. You can scale up, you can increase the value of alpha 1 and decrease the value of alpha 0 and alpha 2 and focus more on H1, for example. Interesting. We'll figure out how to get these scaling factors. We have to think about how we can do that. But this gives you a way to dynamically focus on different parts of the sentence as you need. And this brings us to a very core concept, which is something called attention. And attention is just this wasted sum, right? It's just this idea of being able to scale the different inputs, focus on different word embeddings with different strengths. A question which you will find in your app is to describe this process. So take your time and think about it. Look up a bunch of resources, use the resources doc. To do this, I will give you a bunch of questions and maybe some pointers at the end. Okay, so let's think about this. Remember, words are represented by vectors, right? And look at the title of your first question. It's directionality is important. So let's look at that first. Directionality is important. And let's see what actually happens when you do a matrix multiplication. What happens to a vector when you multiply it with a matrix? Suppose you have this yellow vector, right? This yellow vector. And you multiply it with a matrix WXY. And suppose with that you get a green vector. So what this is actually doing is that it is rotating and scaling this yellow vector. And if you have done the first question in the app, and if you have done the suggested exercise I had given you in the part of the previous video, you would have seen that while playing around with projector TensorFlow, you would have seen that different clusters actually make sense. All the languages are together, all the countries are together, male names are together, female names are together. Interesting. So it seems that you saw that king, man, woman, queen example. So it seems that different directions in the vector space represent different things. Interesting. So maybe with this matrix, suppose you have this vector that's pointing in one direction and has a lot of different components, has information about the you have a sentence, right? You have a sentence, and that sentence has information about whether it's present or past. Maybe there's a component pointing in the present or past direction. Suppose there's a component pointing in some other direction, and all of this information is there in that one vector. Maybe you'll be able to turn it towards one direction and scale that side more. And with that, you'll be able to focus more about that part of the information that's available in this vector. Maybe these are ideas, very hand-wavy ideas. You can think about it, read more about it, right? But the point is vectors have direction and that can be used in some way to figure out what to focus on. Now, one more thing. One more thing which you need to figure out is that similarity could not just be in one particular way. Similarity could be in many, many different ways. So suppose you're writing a story. If you're writing a story and you have a dialogue, you open quotes. It needs to look at similarity with the open quotes to find the closed quotes and close the quote, right? When the sentence is ending. Then suppose it's about, say, you have James Bond somewhere in your article, and it keeps seeing that after James, Bond is a word that comes very often. So it needs to go whenever James comes in the output and it needs to generate the next word, it needs to go figure out that after every James, there's a Bond coming, and maybe Bond is a good word to predict, right? So those are very local. It needs to look at punctuation, figure out punctuation, right? And those are very local, small things it needs to handle at a very microscopic level in language. But if you're generating a story, that's not just the thing. It needs to remember names of characters across paragraphs, right? It needs to remember the plot. Suppose the plot is set in a certain time frame, it's set in a certain time, set in a certain place. It needs to be coherent with that. And on an even broader level, it needs to map the character arcs of the characters, the personalities, and all of that. So there seems to be a need for similarity across varying levels of abstraction, which simply doesn't seem that one layer is good enough. So one way people often handle this is by stacking RNNs or different types of neural networks. You'll see the stacking thing very commonly across many neural networks. You have one set of inputs. It's processed to give one output. Those outputs are passed to another RNN, which uses those outputs as its inputs. It processes and generates some outputs. Those outputs are passed to yet another RNN that takes those as inputs, processes and gives outputs. And maybe those final outputs are the actual outputs which you see. So, and in each of those intermediate layers, each of those stacks, it represents progressively more and more abstract information, suppose. This is something which you see very often in a lot of neural networks. You see it in transformers, you see it in CNNs, in image processing models, where the initial layers, for example, look at edge detectors. Then edges are combined together to make patterns or shapes. Patterns and shapes are combined together to make things like eyes and nose and ears. Eyes and nose and ears are combined together to make dog detectors and cat detectors and human face detectors and all of that. So as you go in more deeper layers of the model, it represents more abstract features, and initial layers represent more basic features. So now let's come back to a couple of downsides of this RNN. What could they be? One is training these happen to be kind of fidgety. They don't train really that well. An exercise, maybe not for the app, sometime later, is to try and write out the backprop for all of this and train one from scratch, where you write all the gradient descent yourself and see that it actually is not very easy to train. You will see very commonly that either the loss goes to infinity or the gradients go to infinity and they shoot up to a very large value or very small value. This is called the exploding gradient problem, or when the gradients become very large, or it's called the vanishing gradient problem when the gradients become very small. So let's try to think about why it happens. So I've written out the equations that are necessary. I've dropped the indices. I would like you to keep the indices, but for interest of space and clarity, I've dropped the indices. Okay. You see that H1 depends on X0 and BH. Right? So now what you need to do is you pass H0 with a bias term BO and the matrix HO with an activation function to get the first output YO, right? And now YO, H0 and X1 all contribute to form hidden state H1. Then Y1 depends on H1 and all the other matrices formed. So what you see is that suppose you're predicting the third or the fourth word, that is Y3. So Y3 is the predicted word y3 cap is the actual word, and you define this kind of loss function that gives you a number for how wrong or correct the neural network's guess for the third word is, or the fourth word is. And as you would know from your prerequisites, that the way this neural network learns is through an algorithm called backpropagation, the gradient descent, where you have this loss curve and it tries to take steps in the direction of decreasing loss. Because from, say, for example, if you remember from 1101 or from PH 1010, you would know that the gradient gives you the direction of steepest ascent up a curve. So the gradient descent algorithm takes steps in the opposite direction, the direction of steepest descent. So to take that gradient, you use the chain rule. So taking the chain rule will be dou L by dou Y. So suppose you want to calculate dou L by dou BH. You take dou L by dou Y3 because that's the first combination, contribution you see. Now Y3 is affected by BO and H3, right? So you have to take that path. Now BH doesn't affect BO, so we don't need to go down that path, but BH affects H3, so it affects that path. Now H3 is affected by H2, Y2 and BH. So we got one term of BH, but you also need to remember that Y2 is affected by BH and H2 is affected by BH. So you need to pass down the chain rule along those paths also. So you'll see very quickly that if you had a decently long sequence, this chain rule will become a bunch of multiplications of different floating point numbers. I mean, there's no point of assuming that they'll be all integers, different floating point numbers. Now, these numbers could be greater than 1 or less than 1. Okay, or it could be a mix of greater than 1 and less than 1. Suppose they are all greater than 1. This whole multiplication of several numbers greater than 1 will make a really large number, right? Or if you had a lot of numbers which are less than 1, this multiplication of several numbers that are less than 1 will give you a very small number at the end. And that's the issue. When you get a small number at the end, because it's multiplying very small edits, then it takes very small steps down the gradient hill and doesn't reach the minima. Or if you take very large steps when all the gradients are much larger than 1, it takes huge steps and jumps out of the hill and never reaches the minima. And these are the vanishing gradient and exploding gradient problems. And this makes it quite fiddly to learn. Okay. Think about it. Play around with the network whenever you have time after the app, and you will find this probably to be quite a fun exercise. So let's see. Again, this is a problem. Is there any way that we can sort it out? Remember that when we wanted to introduce history, we introduced this connection between H0 and H, right? We introduced these connections between the hidden states. Now we want gradients to flow. So we allowed information to pass from earlier time steps to later time steps. Now we want gradients to flow from later time steps back to earlier time steps. Now technically you can flow through this H0, H1, H2 and come back. But you see that there are so many computations that are happening in between. And because there are so many computations that are happening in between, there are so many terms in the chain rule, and that is making the gradient small or gradients large. Right? So what if we just introduce some path that bypasses everything or is minimally affected by every other operation, right? You have one path that is minimally affected. So that allows gradients to pass through easily. And something that allows that is called including a bunch of other introductions, changes in the model, is something called the LSTM architecture, which is the long short-term memory. There's an awesome article written by Chris Ola. He's a researcher at Anthropic right now, and basically a huge voice in the interpretability space. Basically, you can think of him as one of the founders of interpretability. His blog has been cited in the resources doc. Have a look through it. It's called Understanding LSTMs, where he'll walk you through the architecture. This is useful for the second question in your app. I'll not go into more detail about LSTMs, but you can see that this has this direct path, right? This direct path where it is minimally affected, and you can have the gradients flowing down the gradient hill to the initial inputs. Let's look at a few more downsides of this argument. if the sequence is very long, it's possible that the RNN keeps forgetting what comes initially. So in theoretically, like mathematically, you probably could show that this architecture will help you attend to all possible time steps and have context of every input that came so far. But in practice, when you train, this doesn't really happen. Yeah. So this is a big issue. If it can keep into context only small parts of words, it never really learns the entire sentence. So maybe not just words. Suppose you're doing this for music and it has to generate a song. It remembers only say 2 seconds of music at a time. Then it learns only few phrases of music. Doesn't really learn how to start a song or end a song or a chorus or stanza. Suppose it's text. It doesn't learn how to build story arcs. Forgets who the characters are after a point. All of these big issues because it keeps forgetting what comes earlier on. That's one issue. So let's just zoom out and see what all we have covered so far. We started with the simple artificial neural network, which took n inputs, processed them, got a hidden state that knows only that particular n inputs and gives you an output. The disadvantage is that there were no ordering and no sequencing. But the advantage is that there were good embeddings and the entire set of n words were processed in parallel. Now we went to this RNN plus attention model, where you are able to attend to different tokens at the same time. You are able to maintain sequences and you are able to maintain history. But the downsides are now it's serial processing. So it has to process one word at a time. So this makes it extremely slow. If you have longer sentences, it takes even longer time to run. And if, for example, like modern systems, you want to train on the entirety of internet, you can imagine how much time it takes to process each and every word one at a time. So some sort of parallel processing is necessary to train it fast, right? And we also still need to figure out how to attend to different H0, H1. There were mechanisms that did this. I will not get to them. Those are kind of old. We'll only focus on the way it's done in transformers. And we also saw that stacking gives you nuanced representations. That initial layers look at more basic things and deeper layers track more abstract ways. And there's something that happened in practice. Google Translate, for example, about 2016, used to use 7 layers of LSTMs. So when you give your, your Hindi homework for it to, because you didn't understand, you want to understand what it is, you give some text or some menu card you want to translate from another language, it used to pass through these 7 layers of LSTMs and give you an output, which was absolutely crazy. Took a lot of processing power and a lot of training, and was difficult to train like you've seen before. And you would see, for example, it would not be as nuanced if you remember from Google Translate from a few years back compared to Google Translate now, right? And one architecture that was introduced in 2017 by a bunch of researchers at Google is called the transformer. And the transformer is the architecture that runs all of the LLMs that you see today. And it combines a lot of these learnings that you learned throughout the year. We started from 2013 and now we have come to 2017. So you see, for example, this is called the residual stream. This interconnection from the final outputs to the initial layers so that the gradients can flow through. We saw that was a problem. This is called the attention head, right? The attention head, because it needs to look at different parts of the sentence at different times. We saw that was a problem. So there is some way to handle that. We have something called the MLP layer, which is the multi-layer perceptron, which is like a regular ANN that holds information about the world. We have this embedding and unembedding matrix, which we saw the first slide of the first video in our class, that converts these vectors in, like takes these words, these tokens into meaningful vectors. So all of these learnings have been applied to generate this system that is able to do some sort of parallel processing, attend to process multiple words at the same time, but still is autoregressive. It generates one word at a time, but is able to look at all words together. We'll go into this in more detail later. This figure is taken from this paper called a mathematical framework for transformer circuits, which outlines a way of looking at transformers that's useful for interpretability research. And we'll also look at that less wrong article that I had linked in the resources doc sometime. Just for you to remember, directionality is important. All of these rotating and skewing, rotating and scaling operators that we saw earlier. Use this as a clue, and as you look at more resources to think about how to generate, like how to come up with the attention mechanism. There are a lot of resources, a couple of books that you can refer to in the resources doc. Make use of all of them. All the best. If you have any doubts, feel free to ask.